I believe it's still morning in the States. So a very good morning to all the participants from the States, all the way here from sunny South Africa. It's a real privilege to share my research. This is still part of my PhD research, basically, that I completed about 2 years ago. And it's on the topic of Rheo-Mechanics modeling for constructability quantification of 3D printed concrete. Okay, so let's start off with this picture that you guys can see on the right. This was actually, I think this is Wouter's group that printed this. So this column was printed, it's a 3-meter column that was printed in 11 minutes. And you can also see that that column has an eccentricity. So this is really amazing. I think this is still the world record. That's been standing for quite a time. But it's really significant in the fact that if we want to roll out 3D printing commercially, then you need a quick turnaround time. You must be able to print structures fast. You must be able to prevent unsuccessful prints. So because if a print fails and it falls over, you also have the time of cleaning up the materials and then costs associated with that material that you lose, etc. So it's really important that we need to optimize. We always want to optimize 3D printing for basically 3 reasons that are identified. So the first is financial feasibility, as I mentioned, the quick turnaround time. And the second is we want an economical yet highly apt material. So you don't want a material that has too much or too many products in that makes it expensive. And then you don't really need all those extra products and chemicals to actually print the structure that you desire. Secondly, we need to look at the structural integrity. So that is, we have to ensure there's sufficient interlayer bond strength, because that really influences your entire element or object's mechanical response as well as durability performance. And then lastly, we want certainty. So we actually want to quantify uncertainty and ensure that, say, more than 90% of your prints are successful. But that can really be anything. You can decide it if you want it 95%, just as you like. But in essence, if we can ensure this, then it would be reasonable to say that you have quite a superior product. So basically, how can we optimize? And this all comes from constructability quantification. So what I'm going to do next, I'm going to break up constructability, which means it's the process behind constructing an element or 3D printing an element in the fresh state. So basically, we start off with the material characterization. So that's pumpability and extrudability. And obviously, that's the basic function that you need to be able to solve. Otherwise, you won't be able to print, right? So what I did, I characterized that pumpability and extrudability with rheology. So I used the ICAR rheometry that you guys can see over on the right. And then I moved on to filament shape retention. So this is the maximum filament layer height that you can print without plastic deformation occurring under self-weight. So in essence, then preventing excessive deformations, right? So this is crucial if you want good aesthetics for your entire structure. Then I moved on to buildability, and that is where we want to quantify the vertical building rate. So how fast can you actually print vertically, and what is the height that you achieve? If you do that, you can quantify uncertainty, and also you can, to a certain degree, ensure for enhanced structural integrity. So basically, I did this by developing analytical models for these two using mechanics, and in particular more Coulomb, that you also actually simplified to Tresca. But if you combine these two, you get Rheo-Mechanics, and that enables us to basically get an analytical expression for the constructability quantification. So I'm just going to quickly go through all of the models. I'm not going to go into too much detail. This is just to show you how it works. So on the left-hand side, this is basically the graph that shows all the phases that's part of a thixotropic material that gets sheared. So essentially, in the resting phase, you have all the interparticle forces that connects the particles. So it has a structured network. And if you apply a small force, then you get an elastic response. Now, as soon as you start shearing this material, you get shear thinning, right? So the forces start breaking, and then if you continue shearing that even more, you have a completely unstructured state, which then results in a viscous response. So this is obviously good if you want to print. And then if you leave this material standing, so this is obviously after you extruded the material, then it will start to reflocculate to regain this partially structured microstructure. And then if it stands further, you'll get this completely structured microstructure, and then you get elastic response. So if you look at this graph on the right, this is essentially what you get. Your static yield stress corresponds to your structured phase. And then if you shear it where it's completely unstructured, you get your dynamic yield shear stress. And this reflocculation process where you go back from the dynamic to the static is really what thixotropy is for printing. So now we ask, why is that important? And essentially, if I can show you this picture on the left, this is our small printer that we have in the lab. It's about 1 cubic meter. We have a batch mixing system. So we have a hopper where we put the material into. As soon as you start pumping, your material deflocculates because you add a lot of pressure to the material. And that continues in the hose if you have a shear flow. And then so it's deflocculated. Once you put the material down on the bed and then start printing, you remove the external force and your material starts to reflocculate, right? And then you get more strength, so you can actually print an entire structure just using very good material science and not using any accelerators. So basically, if you have to formulate this into an analytical expression, this is just shown on a graph, this is what you would get. And this is what I used as the basis for all the models that follows in terms of the material strength. So moving on to the filament shape retention. So this is just a quick derivation. I'm just going to run through it, but essentially you start off with just a cross section of your filament layer, which you take force equilibrium, and then you have an expression followed by going to look into your stress states that is present within the material. So we assume that there's some degree of friction, base friction. And essentially, if you have friction on the bottom, you get this confined zone that's depicted in the gray, zone 1. So in the zone, you have a triaxial compressive state under self-weight. Zone 2 is the interaction between this zone and the other zone. And in the third zone, which is basically just a uniaxial state, stress state. So there's 3 zones, but just to keep it short, the second zone is the governing zone. So this is the one that I'll focus on. Whereafter, if you have identified this, you have to specify your material failure criteria. So more Coulomb has been used often in the past, but we actually found that there's more accurate failure criterions that we've identified, in particular modified Moore-Griffith expression, but we will release our research on that soon. But for simplicity, we actually just decided to use Tresca, which is very simple to apply in terms of analytical expression. So then you end up with this equation, and this equation is essentially what governs the maximum filament layer height for failure in zone 2. So to show you just the validation, we actually ran a finite element analysis on that, and we found that based on the analytical model, the maximum filament layer height for a particular material that we analyzed was 46 millimeters. The finite element analysis model got, say, about 43. That's with assuming no interparticle friction. And then lastly, we included the interparticle friction, which for our material was almost, say, 35, which is quite high from what I've seen in literature, but you can see you almost get double the height, so it's quite significant. But of course, you will get a lot of elastic deformation, even if you don't exceed that value. So we always actually just recommend to go on the lower value and to exclude the interparticle friction to limit excessive deformations. And on your right, this is just a print that we basically, just to show you guys that if you have good filament control and material control, you can get a very nice finish. The bottom layer was just due to the print path where we add vase mode, so that's not representative of the entire structure. So moving on, so if we have the individual filament layer heights settled, we have to look at stacking them and how that actually influences the entire process. So we start off with your imposed force or your stress. And for printing, this is a stepwise function, but of course we just linearize this to simplify the analytical expression. And the same as for the previous, you get the different stress states within your cross section. If this is the cross section of a filament, you have your triaxial state in the top and the bottom, and in the middle, the uniaxial state. Now, this is assuming an aspect ratio of 2, so your height to your width or your filament layer height is twice the width. But of course, this is not what we print. We go down to 0.5 to 0.3, somewhere there. And you can see that actually what happens is that the two, the top and the bottom coincides, and then you have a very large area that's in a triaxial stress state. So what we found is that it actually, relative to the force, it increases the capacity that this filament layer can bear, the loading capacity, bearing capacity. So what we did, we essentially just normalize the strength at an aspect ratio of 2 using the Tresca failure criterion, and then as you go lower with the aspect ratio, it increases relative to that. So this we applied, and then if you have an a priori condition over here, because of the bilinear model, it just says if this is bigger than that, then use this expression, or otherwise use this one. So that's basically the buildability, which if you plot it on a graph, you get this, where this is your bilinear material strength that we characterize, and that's your linearized building rate, and where these two coincide, you get failure. So we printed a simple hollow column, and we found that we predicted 55 layers, and we achieved 60 layers. So that's about a conservative error of 8%, which we thought was good, and we accepted that. So now where we want to get to is the constructability design model, and this is essentially a combination of all the previous models, right? So we want to design the print parameters. We want to know which parameters must we use in order to realize an object. And we start off with what we have. So you have an object. So you want to print, for instance, a chair or a table, and you know exactly what material you are going to use, and you've quantified it. So, and then we want to determine the optimum print parameters to use, and then prevent premature collapse, because it just has a cost and a time implication that you never really want. So essentially what we need to achieve is that the predicted height is larger than your design height, right? Otherwise the structure is going to fall. So we look at two parameters that we can control. This is your print speed and your layer height. And we say, okay, there's a range between a minimum and some maximum value for your print speed. And this can either be due to limitations of the printer, or it could just be preference that you've experienced by using the printer. And then the layer height, obviously you have a minimum and a maximum. That's also governed by limitations or preference. And we also have to check that this maximum layer height that due to limitations or preference is actually smaller than your individual filament layer height, the previous model that I've shown you. So to give you an example, because this is probably going to show it much better how you can actually apply the model, we start off with the geometry. So we have this wall element. It's a piece of a wall element, and it's 500 mils tall, so half a meter. And this entire structure we want to realize without failure as fast as possible. Then we go on to characterize the material. So you can see we did about five rheology tests. And the first thing you can see, there's quite a lot of variance. The material is very sensitive, we found. But yeah, we just use the average. And you move on to your geometrical input parameters. So the layer width is 30 mils. The path length is, say, almost 2.4 meters, and your design height, as we see over here, is 500 mils. Okay, and then we decided the feasible print parameter range, so 8 to 15 mils. We can't really go larger than 15 because we have a circular nozzle, and you get a lot of rounding, so it doesn't really facilitate bonding between layers. So that's really a range that we try to stick to. And then also the print speed, so we don't really go less than 40 because we have issues with the pump, and they're not faster than 100 for longevity of our printer. And then obviously we have to check that 15 mils is less than the maximum that our individual filament layer height allows, which is sufficient. Okay, so now what we get is what I call a design envelope. So this is a fresh state design envelope, and this is all the permutations that you can go through that will realize the entire structure. So in the legend, you start off with your layer height. So the blue starts with 4 mil all the way to, I think, is 24 mil in that orange-ish color. And then essentially what you do, for instance, if we choose 100 mils per second in your print speed, and you go up to over there where the 4 mil is, and you take it across, you can see that your vertical building rate is 10 millimeters per minute, and you will be able to print that entire structure without failure, right? So you can really choose any of this. You can even go below this, you'll get infinite printing, but you can't choose any combination above this because you'll get collapse. So if you go and impose your design or domain constraints or your boundary conditions, say, so yeah, we chose 40 mils per second and then also 100, and then 8 mils to 15, but 15 doesn't fit in here. So this is the only feasible combination of print parameters that we can use. So obviously in our case, we want to use the optimum or the fastest vertical building rate, which in this case was 87 mils per second and then the lay height of 8. So we went on to print this, and then we saw that plastic collapse actually occurred due to material variability. So at less than 500, which is not what we wanted, but the model was amended via partial factor inclusion to have a 10% probability of failure. So there's a full journal paper on this for details. I'm not going to go into it, but as I've shown, it's basically due to the rheology, the variance in the material rheology that we found that caused this discrepancy. Okay, so just to finish off the hardened state design, how does this influence your hardened state design requirements? Essentially, if you have your design envelope and you have your optimum print parameters, you can really determine your pass time. So how long it takes to print one layer. If you go check on a graph that you must develop a strength or durability parameter on your Y versus pass time, so you have to characterize this, you can go see what will that parameter be, and then the next step is to check if it satisfies the design requirements. So if not, you have to reiterate or you have to use an accelerating agent, but we really don't want to use that because we find that it's, for instance, it induces chlorides. It gives you distinct interlayers or cold joints if it sets too fast, weak interlay bond strength, etc. So the model is easy to apply, but there's limitations. It's obviously because it's analytical, you can't really go vertically out of plane with geometries, and it's also only for plastic yielding failure, but it can be expanded for elastic buckling. And this is just a quick example print that we showed of what we printed. This was basically the maximum that we could print for the shape with the material without accelerator. And so it's the fastest and then the strongest that we could yield this bench. Cool, that's all from my side, and thank you very much for all our listeners. And I'm happy to take any questions.
Thank you, Dr. Kruger, for the very interesting presentation.